Welcome back. In today's video, we are diving deep into an essential topic, capacitors. In previous video, we defined capacitor. In this video, let's learn about grouping of capacitor. Capacitors are key elements in circuits and understanding how to combine them is vital for building more complex systems. So let's take a closer look at how we can group capacitors to achieve the desired capacitance value. Capacitance comes in various sizes and capacitance, but sometimes the exact value we may need may not be available. This is where grouping of capacitors becomes useful. Grouping capacitors allow us to get either smaller or larger capacitance using the capacitors we have on hand. There are two main groups of capacitors, in parallel and in series. Let's first talk about parallel grouping. In parallel grouping, each capacitor's one plate is connected to one terminal of the battery and the other plate is connected to other terminal. As shown in this figure, we have three capacitors C1, C2, C3 joined in parallel. Note here the voltage across each capacitor remains the same. The key takeaway here is that potential difference or the voltage across each capacitor is same, but the charge stored on each capacitor depends on its capacitance. So from this figure we get Q1 is equal to C1V, the potential is same. Q2 is equal to C2 times V and Q3 is equal to C3 times V. Here Q2, Q1 and Q3 represent the charge stored on each capacitor and they are directly proportional to the capacitance of each one. So the total charge Q on all capacitors in parallel is simply the sum of these charge Q1 plus Q2 plus Q3, which is equal to C1V plus C2V plus C3V. If we take the potential common, we get C1, C2 plus C3. This is the equivalent capacitance. This will be the equivalent capacitance of capacitors in parallel. Therefore, Cp is equal to C1 plus C2 plus C3. In series combination, the first plate of the capacitor is connected to the electrical source. So this is connected to electrical source. Then each subsequent plate is the capacitor is connected in series and the last plate is connected to the source again. Here the key difference is while capacitor and series all receive the same charge, but the voltage across each capacitor varies depending on its capacitance. Therefore, we get V1 is equal to Q by C1. V2 is equal to Q by C2 and V3, the potential at charge, is Q by C3. So this is potential across the capacitance 1 is V1, across capacitance 2 is V2 and this is 3 is V3. Each capacitor in series develops a different voltage and voltage across the series combination is the sum of individual voltage. So the total voltage across this combination can be written as V is equal to V1 plus V2 plus V3, which can be written as Q by C1, Q by C2 plus Q by C3. If Cs is the equivalent capacitance in series, then we take Q common. And if we write this as 1 by Cs, so we find the reciprocal of the equivalence capacitance of series is equal to sum of reciprocals of individual capacitance. So we get that 1 by Cs is equal to 1 by C1, 1 by C2 plus 1 by C3. So the equivalent capacitance in series is always less than the smallest individual capacitance in group. Let's take an example of parallel plate capacitor to understand how this works in real world scenarios. Consider the question: the capacitance of a parallel plate capacitor air capacitor is 22 microfarad. The separation between them is D. So this is the parallel plate capacitor, and the separation, sorry, let me write it above, between them is D, and the dielectric medium here is initially L. Now, a dielectric slab thickness D by 2 is put in between the plates. So if suppose here the dielectric slab is put of thickness, calculate the effective capacitance if the dielectric constant K is equal to 5. So this is a dielectric slab of thickness T by 2, constant is K is equal to 5. Now we are given the capacitance of the air as the dielectric medium is C naught, which is equal to A epsilon naught by T is equal to 22, what is this one? Microfarad. The new system can be considered as combination of two capacitors, one with the dielectric slab and the one without it. So let the C1 be the due to the dielectric slab. That can be written as K times A epsilon naught D by 2. So this is 2K A epsilon naught by D, which is 2K C naught. And the second, this part can be written as A epsilon naught by D by 2. Here the dielectric medium is vacuum again. So this can be written as 2 into A epsilon naught by T, which is 2 times C naught. We saw that the effective capacitance C for a series combination can be written as the reciprocal of sum of individual capacitances. So substituting 1 by 2 K C naught plus 1 by 2 C naught. If we take the 1 by 2 C naught common, we get 1 by K plus 1. So C will be equal to 2 K by K plus 1, which is 2 into 22 into 10 power minus 6 by into 5 into 6. We get this to be 36.7 microfarad. Now let's talk about the energy stored in a capacitor. The charging of a capacitor can be visualized as if some external agent, say a battery, pulls electron from positive plate of the capacitor and transfers them to negative plate. Some work is done in transferring this charge, which is stored in the capacitor, in the form of electrostatic potential energy. This energy is obtained from the battery, stored as chemical energy. When this capacitor is discharged through a resistor, this energy is released in the form of heat. Let us assume that an uncharged capacitor, when connected to a battery, develops a maximum charge Q. The charging takes place slowly. The initial potential difference between the capacitor plate is 0 and the final potential difference is V. The average potential difference during the entire process of charging can be written as is 0 plus V by 2. So V by 2. This potential can be written as Q by 2C. Now, the work done during the charging is given by charge into potential difference, which is Q into Q by Tc. So which is half Q square by C. Hence the potential energy is the work done can be written as half into Q square by C, which is half also as half QV, which can be also written as half CV square. This is the energy stored in the capacitor. This energy is stored in the electric field between the plates. The stored energy is directly proportional to the capacitance. The energy stored in the capacitor increases with both capacitance and voltage. However, every capacitor can store only a limited amount of energy, and an automatic discharge will take place when the potential difference becomes more than its threshold value. But be careful, capacitors store energy, and if discharged rapidly, they can release it as heat or even cause electrical shocks. It's especially dangerous with high value capacitors. That's a wrap on grouping of capacitors, both series and parallel combinations. Understanding how capacitors behave in these configurations is crucial for designing circuits with the right capacitance value. If you enjoyed this video, make sure to like, subscribe, and hit the bell icon for more exciting content on electrostatics and magnetism.